Alright, you guys, so here we go. We're going to begin with the next proof on page 254, equidistant chord theorem. So we are given in this proof circle O again, and two chords, CH and chord RD. Okay, and we know again our given statement is that CH is congruent to DR. Okay, so we've got two chords in this circle being congruent to one another. And then we know that OE is perpendicular to CH. And I'll go ahead and mark those on the diagram in a little bit. And then OI is perpendicular to chord DR as well. Okay, and what we're trying to prove is that CH being a chord and DR being the other chord, which are congruent to one another, are equidistant from point O, which is the center of the circle. Okay, so let's go ahead and begin with this proof. We've got given again that these two chords, RD and CH, are congruent to one another. So I'm going to go ahead and mark that right in the middle. And then we know that in order to go ahead and find the distance or between CH to the center and DR to the center, that means we have to go ahead and construct auxiliary perpendicular lines, which represent the most direct and shortest distance between DR and CH to the center of the circle O. Now that I've marked my given, I'm going to go ahead and construct some additional auxiliary lines here, because after all, what I'm trying to prove is that these two dashed lines or line segments are congruent. So I'm going to go ahead and add to my picture a couple more things that will help me construct some triangles that, if proven congruent, I can go ahead and conclude that these line segments, OI and OE, are congruent as well. Okay, let me go ahead and mark I and E. Okay, well, this triangle right here that I have constructed, I can't really prove yet, okay? But what I can do prove congruent is a bigger triangle in this circle right here. So here we go. I'm going to go ahead and connect all of these endpoints of the chords to the center of the circle. Therefore, I have just created two bigger triangles, DOR and COH, congruent to one another by SSS, or side-side-side triangle congruence theorem, which says if two triangles have three sides that are congruent to another three sides of another triangle, then those two triangles are congruent. Now, this side is congruent to that one, radii in the same circle. This side is congruent to that one, radii in the same circle. RD is congruent to CH, and that's because it's given. So by side, these two bigger triangles are congruent. Well, how is that going to help me? I want to use this information I have just concluded to go ahead and create some more congruent parts that will help me prove any combination of two triangles, one from each of the two bigger ones, congruent to another one. So here we go. I'm going to go ahead and mark this with a star and mark this one with a star and try to prove that these two triangles, IOR and EOH, are congruent to one another. What I had just proven previously is that these two bigger triangles are congruent. So I can go ahead and conclude some additional information. First of all, I need to know that IOR and EOH are both right triangles because of the given and the perpendicular line segments that create right angles, which by definition give me right triangles. I also know OR and OH are both radii in the circle. They're congruent, but they happen to be the hypotenuse of both of these triangles as well. So now I've got a hypotenuse congruent to another one in two right triangles. What I also now have is the fact that I had just proven this angle congruent to that one by CP/CTC, because they're both corresponding parts in two congruent triangles. Now that these two triangles have a hypotenuse and an angle, I'm going to go ahead and use the hypotenuse angle right triangle congruence theorem, which allows me to say these two triangles marked with a star are now congruent. Since these two triangles are congruent, then I can go ahead and add that by CP/CTC, these two dashed perpendicular segments are congruent as well. And since they're congruent, that means they are equal in length. And the reason I'm converting between congruence and equal measure is because I'm trying to prove that they are equidistant from point O, which is the center of the circle. So now that these two are the same measure or length or distance, then I can go ahead and safely say that point O is equidistant from both chords DR and CH, which proves my theorem, equidistant chord theorem. If two chords are congruent within the same circle, those two chords must be equidistant from the center of that circle.